hardware. Let's go. Boom. FSM 1 hot. Following state machine 1 input and 2 outputs. Okay. Suppose state machine 1 hot encoding, where state 0 to 9 correspond to this. The outputs are 0 unless otherwise specified, so 8, 9, and 7. Implement the state transition and output logic portions. Okay, so given state, create next state, and then by inspection, assuming 1 hot encoding, we'll test non-1 hot input to make sure you're not trying to do something more complicated. I see. Because I can't see the diagram, it's like... Next state 0 is just gonna be if, oh, that's just yeah, this is the only... Oh, no. I see. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. No, 0, 1, 2, 3, 4, 7, 8, 9 has zeros going to S0, and that's all the things that go to 0. So actually, we can just do S state of 4 to 0. So any of these and comma state of 9, 8, and 7. And not in duplicated. So and the 5 plus 3 is 8, which makes sense because there's 10 states and 10 minus 2 states point to S0. So bitwise, this says, given any of these bits ended with not and maps to S0 as the next state. Now, then we just do a reduction OR to take care of that. This is probably the more complicated state. And I see a similar pattern up to 4, so like, well, S1 is different actually. Or, so this arrow points to here, and then also if state of 9 or 8 and like this. So either of these combined with in goes to S1. And then next state of seven to 2 is going to be state of 6 to 1. So 7 requires S6 and 1. S6 requires S5 and 1, 5. 4 all the way to 2 requires S2 and 1. So there's only one arrow, so there's no reduction or anything. And this is just 6 bits of in. So that's S7 that's handled, and now let's take care of, actually S7 is a special case. So, or so the MSB has 6 and in, or it has S7 and in. And that should take care of 7, 6, 5, 4, 3, 2. 1 is handled here with 3 inputs, and 0 is handled here with an input from 4 to 0, as well as 8, 7, 8, 9. Okay, so now let's handle what goes in S8 and 9. As far as I can tell, there's only 2 arrows, so equals state of 6, 5, and 2 of not in goes here. So that'll be the next state. And then assign out 1 equals state of 8 or state of 9. And then assign out 2 is state of 9 or state of 7. That's like actually like quite a bit to implement. Okay. We then assume that this is byte 1 of the message and signal the receipt of a message. Once all 3 bytes have been received done, FSM should signal done in the cycle immediately after the 3rd byte. So in is 1, 2, 3, and then the 4th byte. Huh? This is pipelined. Okay, cool. I don't get what error means. When error occurs, note that this is not the same as a 1xx sequence. Overlapping sequences are not allowed here, so I'll say synchronous reset. So So for example, I see this. I want to go to byte 0. And then I'm here. I want to go to byte 1, byte 2, and well, I guess kind of a misnomer. I always assume I'm byte 1, and then if I encounter this, then I go to 2, 3 vacuously, and then 3 goes back to 1. But if I'm equals 3, I set done in the next cycle. And I'm back to byte 1. And if I'm back to byte 1, I can continue this. And so in this case, I ignore this in. Alright. I don't need next done then, so this is actually just byte 3. Next state is byte 2, next state is byte 3, state is byte 3, done is asserted. Okay. And Okay. Yeah, I wasn't sure because of this. And that's true. I only care about byte 3. Oh, this is a continuation of last problem, so. Okay, I deleted it. Crap. Okay. Now that you have a state machine that'll identify 3-byte messages, add a data path that'll also output the 24-bit message whenever a packet is received. Okay, well. This is sad. Okay, so let me, since I deleted it, I need to do that. enum byte 1, byte 2, byte 3, state, next state, and then case, state, and case, and then just do byte 1, then next state is simply going to be byte 2, otherwise byte 1, byte 2, byte 3, byte 3, byte 3, byte 1, and then always at pause edge clock begin, if reset begin done is this, and state is this, and else begin done is going to be if state is byte 3, and then state is going to be next state, and like this. Let's do this again to make sure that works. Okay, great. Next is I'll also need this, which is a packer. So this is don't care, so I can just keep shoving 7, 0 in byte 1 in here. And then on byte 2, I can shove it to 15, 8. So byte 1, I'll just shove it like this, but out byte is 24, like that. So every time we're stuck in byte 1, we'll just keep starting out with this. Otherwise, if we're byte 2 or byte 3, then we simply do this. So we shift this up by 8, and then we also OR it with 16 plus 8, so 3 bytes. So byte 1, next is 2, next is 3, and next is 1. But byte is 3, so byte is 3, we would still, okay. So here we would shift 8, we would put 8. So here out bytes would be 8. Here out bytes would be 8 plus this 8 shifted. And then ORed with this 1 here. And since byte is byte 3, next state byte 1, we would still keep doing this for 1 more. I think that is right. If there's a solution, I wonder if there's a better way to do this. Okay, well, I'm not gonna delete it because to use 1 bit, 1 start bit, 8 data bits, and 1 stop bit. The line is also at logic 1 when nothing is being transmitted idle. What does that mean? And then find when bytes have been correctly received when given a stream of bytes. The stop bit doesn't appear when expected. The FSM must wait until it finds a stop bit before attempting to receive next byte. So I guess in, and then we in and then nothing, and then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, and on the 9th cycle we should get in, and then we do a stop. In one derivative, and then we don't find it on the 9th cycle. So we're idle again. Okay. State is just idle, and else begin state is next state. If here I go to start, I need to know like this many cycles ago if I have a, okay. If I'm at data and this next cycle is like stop, well, yeah, detect this next cycle is stop, and then stop, I assert this. So if I'm data and I'm ninth cycle and this is like this, next cycle is idle, and then idle can receive us, like idle can receive this. If I see this, then next cycle I go to start. Otherwise stay at idle, like here. Now I see this next cycle, I go to, so next is start, and then this is start. Start. If I see a ninth cycle, actually next cycle is start, but then I also need to assert done next cycle. Start happens if here next state wants to be start, but then here it says what? Start still. So I have a one, I transition next state to start, and then only if I detect a 0. So this is start, and next state start, and then if it's 0, then I go to data phase, right? So next state start, next state start, next state start, next state data. It's just a 4-bit counter such that if I go to next state, data, I start 0, and then 0, 1. So 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 and in is when I assert stop. Eight and in. If 8 and in, then do that. So transitioning into data, we go to 0. Otherwise, if next state is data, then we continue doing this. Otherwise, I'm in some other state, so that. So transitioning data does a reset. And if we're already if we go to this case, it means that we're data and the other thing, so state equals data. So you just keep incrementing it, and otherwise, next state isn't data. We don't really care. So next count is 8 and zero, 1. So 0 is here, and oh, that's actually count. Count is 0, 1, 2, 3, 4, 5, 6, 7, 8. So count is 8 and in. If count is 8 and in, then next cycle stop asserts. And count won't ever go to 8 if we don't transition to data. Okay. If count is 8 and no in, then we're not done. Okay. And all right. If count 0, 1, 2, 3, 4, 5, 6, 7. Hmm. This is tricky because 0, 1, 2, 3, 4, 5, 6, 7. Eight. Because I kind of want, I guess here, if it's 7, like, I kind of want to, if it's 7, I want to go back to idle. Because if it's 7 and I go back to idle, idle will meet this in to go to start, and then it'll meet the 0 and go to data. But the issue is, when I do this, then when count is 7, next state is not data. Mm-hmm. So this I handle the case where this transition goes to 0, and then 1, 2, 3, 4, 5, 6, 7. The next state is no longer data but idle, but state is data. Yeah, next state is idle. So actually we keep trucking on, we do 8. And now the current state would be idle, which means we just go back to 0. And then we still preserve this 8 so that we can do this and in. And then because we go back to idle, then this isn't true. Well, yeah, this can't be true. This idle can only go to start. This can't be true, and this won't be true. Oh, I need to assign output, which, oh, yeah. Line 24 has some issues. Oh. Ah, okay, whatever. That's weird because reset has in as one is kind of weird. Okay, done. Let's backwards this. So done is count. Count is based on next count. And next count is going to be based on next state. Here we should have state idle, and because we just do this, and so next state is just gonna be in and not reset. So reset is clipping, ignore it, but apparently so at reset equals 1, it should clip this to idle, or at least I thought. If it stays idle, then this should just output 0. So let's say this isn't oh, the reference says it is done. What? No, this won't compile. So here then, next state is always going to be start if in is 1. And then so if reset and in is 1 held 1, say reset is went to 0 and in went to 0, but then the previous cycle in was 1, the next state is yeah, I don't clock it. They want this spec is kind of bad because they're saying they want to consider inputs at reset. Then what? Why would you design a chip like that? Yeah, that's ridiculous. So here if reset, we're stuck at idle, and this says start. So this says next state start. So the issue is when reset goes to 0, in also goes to 0, and well, what is next state? Because next state starts at x, right? Like it doesn't start at 0. So they want state to be reset agnostic. Okay. Seven, 6, 5, 4, 3, 2, 1, 0. So 1 and then 0 and then 8 cycles and then 1. So 1 and then 0 and then so 1, 0 and then 8 cycles. 1, 2, 3, 4, 5, 6, 7, 8 cycles and then wait 1, 0 1, 0 1, 2, 3, 4, 5, 6, 7, 8 1 1, 0 1, 2, 3, 4, 5, 6, 7, 8 I'm actually not sure what this edge says. So basically all we're trying to identify is 1, 0, 8 cycles of data, and then 1 again. So 1, 0, 8 cycles of data, because count always starts at 0. So 8 cycles of data, count not equal to 7. So if count is 7, then that means we had a cycle of, so we start cycle 0. We had a cycle of 0, cycle 1, and then all the way up to 7 inclusive. So that's 8 cycles, and we go to idle, and if idle says so when we do go to idle, we have 8. And if it's in, the next cycle is done. So boom, 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 boom. But what's going on here? Here is saying we have done, then that means the previous cycle was 8 and in. So 7, 6, 5, 4, 3, 2, 1, 0. So next count is 0. So count is 0. And what if we are in data already? Like, what if the state here is data? Then we don't. So 8. Six, 5, 4, 3, 2, 1, 0. Count is 0 here when we have 1, 0. So one, 0, right? So if we were at idle, then so basically I'm a cycle too fast, basically. It's frustrating. So I'm a cycle too fast, but why? So if I'm at idle and this in, then the next state is start. And if my next state is start, then this is not true, this is not true. And this is not true. So it should just be 0. And this is 0. So state is equals equals. So then I should go to data. Okay. So then this should hit, right? because next state is data and my state is not. Data. So the next count should be 0. So like here, I feel like the next count should be 0. And then, so count is 0, 1, 2, 3, 4, 5, 6, 7, 8. But so if this is 8 and this is 0 and this is 1, then that means, right? Because if this is 8, 7, 6, 5, wait, 8, 7, 6, 5, 4, 3, 2, 1, 0. Then here we're going from, so next count here is 1 from 0, and next count here is 0, next count here is 1. This is actually extremely hard to debug because you can't print anything. 8, 5, 8, 7, 6, 5, 4, 3, 2, 1, 0. And so the next count here wait, 8, 7, 6, 5, 4, 3, 2, 1, 0. So next count is 1 here. So next count is 0 here. So next count is 1 here only if we hit this case, meaning the next state is data and current state is data, or the state is data and the next state is idle. Suppose the latter, if the state is data and the next state is idle, if my state is data and my next state is idle, then I'm like here. But if my state is data and my next state is idle, that means count must be 7. So how does next count end up as 1? And if next state is data causing this, so my count was 0 for some reason, meaning I am next state data and my state isn't data, but my next state is data and my state isn't data, there's only this start state. Start to data is the only thing that satisfies this. And start state can only be hit if we see a 1, 0. So idle 1, 0. But then if that's the case, next count would be 0, not next count would be 1. I'm wondering if there's a better way to do this so it's less kind of confusing. If count is 7, then it should just be 0 next. And otherwise, if state is data, not next state, like state is data, then this is the only time that it should increase. Otherwise, default to 0. So this is a bit cleaner because this says just 0, 1, 2, 3, 4, 5, 6, 7, and just go to 0. And here it says the state is data, and whenever state is data, the next count is 1, so 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And this will go to 7. Here my done is when I'm actually at idle. previous state, so here I go to idle because count was 7. So previous state was data, I am idle. And inferred latch on next state. Oh yeah, because I can't. Yeah, this is the same thing, so I think there's something I'm not. And that's 1 0, which is true, and then 1 2 3 4 5 6 7 8. No, that's like way too far though. So 1 0 1 2 3. So 1 no 1 0, and then 1 2 3 4 5 6 7 8 data. And I don't get how this is happening at all. So this is when data starts. This is when data ends. So I need to look at this cycle. So why is this happening? So the assumption is, well, the reference is there's no done at all, right? So it's not even a cycle, or there's no, this doesn't happen. So if like stop bit isn't found, what happens? So count is 7 and I go back to idle. go back to idle, and I stay in idle. But what happens to the count? It stays 0. Because if I go back to idle, so here I'm in idle, and if I go back to idle, well, first, if it's 7, we go back to idle in the next cycle. And also next count is 0. And if we're in idle, then we stay at 0. So but if this is happening, this is very explicitly saying that previous state is done. So, sorry, previous state was data. And if previous state was data, that means the count here was 7. If it's not 7, it stays in idle. If it is 7, it goes to idle. So then we say this is 7, right? 6, 5, 7, 6, 5, 4, 3, 2, 1, 0. This is count. This is just working backwards, right? Because if state is, then count plus 1. Then working backwards, what goes to data if we're at start and in is 0? So this is saying this is start and in is 0. Start and in is 0. And then so working backwards once again, then if, right, so how do we go to start? We go to start if we're in idle and in is 1. And state equals idle and in. I see. So here there's an extra cycle. So previous state is data. Actually, that's not right? So it's true in this cycle that in is 1. And then so actually this done here is driven by this cycle's information. So here it's saying that with respect to one cycle before done, okay, then we do have an in, and it means we're at idle, and then it also means that, I'll just write cursive, idle, and then this is done, or data. Oh my god. So previous state is just, you know, the state a cycle ago, so it's data. And I can go to idle if count is 7 here. So count equals 7, next state is idle, so this must mean this is 7, this is 6, 5, 4, 3, 2, 1, 0. And we know this because if state is not data, unless next count is nope, it's just next state. Unless this next state latch screws up everything, and we're at the completely wrong. I don't think that's it, but I want to see if there's an inferred latch. Okay, so let's keep going. So if state is not data, we basically always have next count is 0. So next count is 0, and so next count here is 1, next count 2, 3, 4, 5, 6, next count is 7, count is 7, and then we go to idle, right? And then so here, you know, can we deduce that this is the only entry point? So then we say this is start. Right? But my in is 1. So how do I get to data here? I can only go to data if it's 0. Actually, this is interesting because if count is 7, I want to go to idle. And I'm at data. But next count is 8. But then if count is 7, we reset to 0 anyway, so. So if in is 1, and we're at start, then we have to stay at start. So if this is 1 and we're at start, then this can't be done. And this isn't 0. Here it's saying, so there's 2 entry points of data, which is data to data and start to data, but because this in is clearly a 1 here, we can't go to data. So this state can't be start, right? Because in must be 0 for us to transition to data. So I'm guessing this is data somehow. And but then I don't get it. I don't get how this count is wrong. Count starts at 0. And the only way for the count to move is if I'm at state data. And I'll keep adding this count until it equals 7. And if I'm at 7, I restart at 0 until I'm at data again. Yeah, if I'm not at data and my count isn't at 7, then my next count is always 0. So it's always clipped to 0. So is there a way for me to like if I'm at like start state, I'm presumably at next count 0. And if I go to data, then data starts at 0. And if I have data, then count +1 is data, 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 data. I don't, yeah, this probably doesn't do anything. But, probably I'll just try again tomorrow, because I have no clue what's going on here. And I don't know how to print out any more stuff on the waves. Oh, I guess I'll check one last time. So like done is asserted here. This is based on previous state. So it means this thing, one cycle earlier, it was 1. Then it must mean that the previous state is data and current state is idle. But if that's the case, then that means that in the previous cycle, the next state is idle and the current state is data. But then that can only happen is if count equals 7, right? And the only entry point, if I'm not mistaken, for count, so count is next count, and the next count can only, so if it goes to 7, it is 0. Next cycle. So but to get to 7, this is the only way, which means my state is data. So if I'm at data, then count is 7, count is 6, count is 5, count is 4, count is 3, count is 2, count is 1. Count is 0. And can count be -1? I guess this part when count is 0 is kind of where like I'm not 100% sure what happens before that. I don't think it's this first case where count is 7, so I don't think it's like 7 to 0 and then repeating forever. And the reason why I say that is because if count is 7, we'd go to idle, not data. So if this was 0 and so then I think it's this case, but this case just means that or this is 0 and this is F somehow. Like state is data and F plus 1 is 0 again. But as soon as I'm 7, I jump out of idle, and as soon as I'm 7 and my state is data, the next cycle, this 0 gets propagated to count. So count is 0, and then also we're in idle. So idle count 0. I don't get why this is so hard. So we agree on the fact that if we're in data, we always just be able to go to idle. Then this count is 0, and this can't be start. So what is it? Can't be idle. Idle can't go to data. So it has to be data somehow. And can data be stuck at 0? So this is non-7, and this is data. That must be +1. So I guess I don't get how this ends up at data state. And it's unclear what happened before for it to transition into data state. I don't know if what I'm saying makes sense. So count is 0 here. And if count, I guess could be 0 here, but if count is 0 here, then like if count was 0 here, then but then if this is data also, like if this is data also implies count +1, right? So then this has to be -1. But if this was -1, then somehow it wrapped around and I don't know. All right, I think that's it.